So again, this visual at least should start bringing some clarity. So we are looking at a sinusoidal, let's say, voltage. Okay, here let's look at the center figure. This is going on in a circle for certain elements. Okay, for given any circuit, the angle between voltage and I is always preserved. If this voltage moves here, okay, as it is oscillating, okay, voltage at some other time, the current at some other time would be along that direction. That is also moving in a circle. And can we also guess the element, what kind of a circuit we are looking at based on this? Voltage and current are exactly aligned. Okay, resistor, excellent, thank you very much. Okay. Now, there are again certain ideal elements where if voltage vector is along like this, at that instant, at that snapshot, the current vector is along like this. Okay, and this angle specifically is 90 degree for that ideal element. Can we guess that this element over here? We have the inductor over here. Okay, and the point of this representation is at a slightly later time, voltage vector would have moved here. Okay, current vector would have moved here. So we are completely forgetting things happening with respect to time. We are only concerned about, given the voltage vector, do I know the current vector? And do we know it's actually magnitude? Notice the voltage and current will have different magnitudes. It's not the same magnitude. Okay, voltage is like this, current is like this. And then finally we have a capacitor. Again, the phase difference between voltage and current is 90 degrees. Okay, if you tell me what the voltage vector is, or the complex number corresponding to that, the phasor, I will tell you what the current vector is or current phasor is. As simple as that. So we have gone rid of this oscillating thing. We are only talking about what this complex number and what that complex number is. And at this point, there is a quick, simple mnemonic over here. Okay, so this thing we have, civil, right? Yeah, this is an inductor. Notice in an inductor, the voltage is leading the current vector. Okay, and this mnemonic kind of helps. We have CIV IL, right? In an inductor, in an L, inductor has usually representation of L, right? We have voltage leading the current. And notice with respect to current, voltage has a positive phase, specifically plus 90 degrees. This is leading. In a capacitor C, okay, current is leading voltage. With respect to the voltage vector, we have the current vector. Or you could say voltage is lagging behind the current. Okay, this again is plus 90 degrees. And what this means is, and for a resistor, of course, one is aligned over the other. What this means is, if current is like this, or voltage is like this, current will also be like that. Will have a slightly different peak based on what the resistance is. Okay, for an inductor, if voltage is like this, okay, current is kind of lagging behind. That is, it has a minus 90 degree phase. How should should the curve be shifted or delayed, advanced or delayed? If this is voltage, the current here in an inductor, should it be advanced or delayed?
Sir, advanced.
It is actually delayed. Okay, this is notice minus 90 degree, right? You take V, with respect to V, you do a minus 90 degree. So the function, if you start scratching your head here, there is, or you open the tap here, the water starts flowing here, like this. Current will be delayed. Notice the current is kind of lagging behind. Okay, voltage is leading. On the other hand, in a capacitor, the same thing. If you have the voltage like this, okay, the current will be advanced. In that case, the current will be actually like this. Current will be like this because this is plus 90 degrees. Or the current kind of started, current curve kind of starts here with a, pi by 2 advance. Again, notice the beauty. Here, if you tell me the voltage, I know the current as far as I know the resistance, right? I can do that for any instance. The same case here also, if you tell me the voltage, I can tell you the current a little later. Okay. If you use phasors in time domain, there is a delay. In phasors, it actually, with respect to this vector, this will have a phase. Okay. So this delay in time domain kind of becomes a phase in this complex number notation. So if you tell me this value, I'll tell you this value just like that. And typically we'll tell specific peak values, we can tell this peak value. Similarly, if you tell me what this peak value is, I'll tell you this peak value and when that peak will happen. Okay, if that, okay, sir, this phasor confusion was slightly confusing, at least this current figure should at least illustrate what we are referring to. Tell me this peak, I'll tell you that peak, and I'll also tell you when that peak is happened. That relation becomes very, very, very easy. Okay, again, without going into a lot of math, we have, three elements, right? We have a resistor, we have a capacitor, and a current. Here, voltage is I times, let me write it as, R times I. Okay, for AC circuits, there is something like resistor, okay, for even capacitors and inductors. So you can write a direct relation between the phasor voltage here and the phasor current here. Notice this complex number, and there is one more complex number or one more constant that's a complex number that connects this number and this number. That we are going to refer to as Z or the impedance. And because it's a capacitive impedance, I'm going to put ZC. Notice, okay, V is a complex number, I is a complex number. The relation between V and I is one more complex number, multiplication. Similarly, for an inductor, if you tell me V, if you tell me what is I can tell you what is I. Complex number that connects the two. This case is, it's an impedance. Let's call it ZL because it's corresponding to impedance of O. Okay. Z plays the role of R. So whatever you can do with the resistance, all of that, all the tools you can start doing with Z. Sir, can I do voltage division? Yes. Can I do current division? Yes. Can I start applying Kirchhoff laws? Yes. Node analysis, mesh analysis, all those. Can I do delta to Y transformation? Instead of R, I am given this complex number Z. Can I start doing that? Yes. So all the tools, okay, can be applied. And specifically this complex number, again, the math is given in the recorded videos. ZC, what is ZC? Can we be slightly specific about this complex number? Can we also be specific about what this complex number is? If the capacitance is C, what is this complex number? Okay, again, if I write it down, you might start recognizing it. Take the capacitance, 1 over that with a j omega term. So notice this impedance depends on frequency, is a complex number, so there is the j over there. C is a constant capacitance. And here it's going to be j omega L into this current. So ZL here this is 1 by j omega L plays a role of resistance. Okay, sorry, j omega C plays a role of resistance. J omega L plays a role of resistance for an inductor. Okay, how this happens, I think slightly better explained in the recorded videos. Let's not spend time there, but let's just start applying this impedance, again, see in the numerical examples, start applying it and, start solving circuits. So notice we have V is IR Okay, for an inductance, V is L di by dt, and here I is Q is CV, right? C dV by dt. Okay, this is what we have been studying till now, but time is not all that convenient to look at AC circuits. In the frequency domain representation, or the phasor representation, we have this phasor. Okay, this is a real number. All three numbers are real numbers, so no issues. This voltage at an angle of 0, okay, that current at an angle of 0 is that resistance that's purely real. Again, this is just VSIR. All angles are 0 here. Here V is J omega L into I. Okay, and here V is 1 by J omega C into I. Okay, notice if you know some Laplace transform, okay, you can start. So taking a derivative in time domain corresponds to multiplying by J omega. So J omega C into V equals I, right? Continuing, this notation, notice d by dt actually kind of becomes J omega into that variable. Okay, and integral of something, okay, this becomes J omega V, and integral of something kind of will become 1 by J omega into V complex V. Again, you could also quickly see that if you write V as G power J omega T, you can see why if you differentiate with respect to time, you get J omega. Or even notice, if you know Laplace transform, there is that variable derivatives can be converted into simple algebraic expressions, right? Instead of S, we have J omega. Again, integrals can be converted into algebraic expressions. It's a very, very special case of Laplace transform, specifically Fourier transform.